Alright, Assalamu alaikum. So in the previous lecture I finished off my discussion with the energy of a magnetic dipole placed inside a magnetic field. Now if I have an electric field associated with each point inside the electric field, there is a potential. And if I have a test charge plus Q that is placed at that particular point inside the electric field, there is an energy associated with this system. So what is this system? This system is a charge that is interacting with an electric field, right? And the energy of this system, it's the electric energy, is given by the charge Q that we place on side this point and the potential at this point. Correct? This is how we've defined our potential energy, electrostatic in origin, due to a charge that is placed inside an electric field. Likewise, if we have a magnetic field, in an arbitrary direction B, and we place an equivalent to the charge. Now there is no equivalent to a charge, there is no magnetic monopole, so the unit of a magnetic moment, the unit of magnetism, something that responds to magnetic fields, is a magnetic moment, or a dipole moment. So we place a magnetic dipole at some point P inside this magnetic field. Now this dipole in itself, even though I've drawn it as a circulating current, there could be different origins of magnetism, but for the purposes of a model we've chosen a circulating current, and associated with this current there is a magnetic moment, mu. So when this object is placed inside the magnetic field, there is a corresponding magnetostatic or magnetic potential energy associated with this system, an external object that has been perched at a certain point inside the magnetic field, and that energy U is given by the dot product of the magnetic moment with the magnetic field. And this minus sign ensures that whenever this magnetic moment is parallel to the magnetic field at some point, the energy is lower. So that's why if you have a magnetic field, dipoles tend to align in such a way that their magnetic moment is parallel to the magnetic field. This will lower the energy of the system. So if a magnetic moment is on its own and it's pointing in some arbitrary direction, which is non-parallel with the magnetic field. So if the magnetic field is upward, the moment is in this direction. So what's going to happen is that this is a high field configuration, a high energy configuration. So this magnetic moment will tend to align itself with the magnetic field. And how will it align itself? It will experience a torque. And that torque will rotate this magnetic moment in such a fashion that the final magnetic moment points parallel to the field. So this is the energetically favorable scenario that would happen. And the torque, as we looked at in the previous lecture, is given by this cross product of the magnetic moment with the magnetic field. Now this is something that we've already seen in the previous lecture. Now this magnetic moment can be a circulating current, it can be a loop of wire, it can be an electron which possesses orbital angular momentum, it can be the spin of an electron or the spin of a proton. And I'll have more to say in today's lecture about this in today's lecture. Please shut down your mobile phones. Now let's look at certain applications of this concept. Suppose I have a magnet, a conventional magnet, like a bar magnet, which is generally thought to, it is believed that it has a north pole and a south pole. But this magnet is really a large dipole. The Earth itself is a large magnetic dipole which possesses a magnetic field. So if you look at the magnetic field due to this bar magnet, there are magnetic lines coming out of one end. There are magnetic fields inside matter. Remember, electric fields generally do not penetrate into conducting matter in electrostatic conditions. There's no electric field inside conductors in static conditions. However, magnetic fields in static conditions can penetrate into matter. So inside this material, which is a magnet, there is a magnetic field. And if you draw a pattern of the magnetic field, this is what the magnetic field will look like. Okay, and it will curve on itself because you have to satisfy Gauss's law for magnetism. Now suppose I have a magnetic dipole. Let me rub down this line, okay? Now this is the magnetic moment of a dipole, mu1, mu, alright? Now this dipole is pointing upwards. And this position, let's call this position P. Okay, this is the position of the dipole. And the distance is measured from the tip of this magnet. So this point is z equals 0. And as you go up, z goes up. So at point P, at this particular point, there will be some energy associated with the dipole that has been placed inside the magnetic field. Now consider another point Q at this level. Now what's the energy of this dipole placed at this point P? You have to know what the field is at point P. So at point P, let's call the potential energy U1. U1 is given by minus. Now suppose the magnetic field is still pointing in the upward direction, so you're along the axis of this bar magnet. So the magnetic field always is pointing in the upward direction. So at this point, suppose the magnetic field is B1. Alright. Now you have to multiply this B1 with this magnetic moment, mu. And since the angle between mu and the magnetic field is 0, so cosine of 0 is 1. And I insert this minus sign because there is a minus sign in the formula. So this is the potential energy of this magnetic moment at this point P. Now if I were to place the same magnetic moment at another point Q, which is now closer to the bar magnet. So at this point, the potential energy U2 is going to be minus mu P2. Now which of these magnetic fields is stronger? Which one? B2 is stronger because it's closer to the magnet. Now if I were to find out U2 minus U1, which is the difference of the potential energies, this difference, it turns out to be minus mu B2 minus B1. Now B2 is larger than B1, so this is positive and this is negative. This means that U2 is smaller than U1. So the potential energy is smaller here and it's larger here. So if the magnetic dipole, which is pointing in this particular direction, is closer to the magnet, its energy is smaller. The potential energy is smaller. So if we were to bring the magnet, if we leave the magnet here, this dipole here at point P, it will be attracted towards the magnet. So that it comes towards the magnet and lowers its potential energy. Alright? So this dipole would tend to come from point P to Q because this lowers the energy of this system, the potential energy of this system. And when it lowers the potential energy of this system, if you look at the work energy theorem or the principle of kinetic energy, of energy conservation, this delta K plus delta U must equal 0. There is nothing external in this system. The dipole and the field form the system. There is no battery or external source of magnetic field that is being applied. So this rule has to be satisfied. But delta U is given by this. So delta K, which is the change in the kinetic energy as the particle goes from U point P to Q, is given by minus delta U. And this equals minus U2 minus U1. And this would simply equal mu into B2 minus B1. Now this is a positive quantity. So as this dipole shifts from point P to Q, so you leave the dipole at point P, it just is attracted towards the bar magnet. It lowers its potential energy in the process and increases its kinetic energy with the corresponding amount, because energy has to be conserved. So this bar magnet will attract this dipole towards itself. Now this dipole could be another bar magnet, a tiny bar magnet. So we can have attraction and repulsion between bar magnets, or between two magnetic materials of any kind which have some magnetization. So suppose we have two bar magnets. Let's consider the situation in which we have two bar magnets. So there is a so-called north pole and a so-called south pole. And then we have a so-called south pole and a so-called north pole. I'm using the word so-called because these poles don't really exist. So what this bar magnet really is, it's a magnetic moment. And the direction of this magnetic moment is from south to north. Just like we define an electric dipole moment. Here, the direction of the dipole is from the south to north. So the magnetic field due to this magnet goes like this. Just comes back in like this. Okay? So this is the magnetic field that is produced by this bar magnet, or the field that is produced due to a magnetic dipole. Now this magnetic dipole can be modeled as a current carrying loop. Okay? But that's only a model, remember. So if you were to find out the magnetic field due to a bar magnet, we will find the magnetic field due to a current carrying loop or due to a solenoid. Many current carrying loops stacked together. Now this bar magnet produces a magnetic field, and if you have this configuration, which exactly corresponds to the configuration that I've drawn at the top, you have a dipole moment, which is the source of the magnetic field pointing up, and you have another object whose response you're trying to determine in the presence of the magnetic field, and that's also a magnetic moment pointing in the upward direction. So this situation actually represents this physical situation. And this bar magnet, of course, it will be attracted towards this bar magnet, which has been placed in a rigid support, so we don't allow this to move. If you allow this to move, this bar magnet is going to drop down and lower its potential energy. And when it drops down, its kinetic energy goes up, so it accelerates. Its speed goes up. Now, this also means, since the kinetic energy is going up, this object is accelerating. So there must be some force acting on this object. So let's find out, how does this force depend upon the distance between these objects? How does this, so if you move this magnet far away, the attraction will be hardly felt. If this magnet is closer, the attraction will be extremely strong. So we would like to find out an order of magnitude estimate of how large that force is. Okay? Abu Zar, please stop talking. You're constantly disturbing. So now if you would like to model this situation, how do we model this situation? So we draw two magnetic dipoles. So we draw a dipole for this and we draw a dipole for this, so that we can actually reduce this problem to what we've learned so far in the class. So this bar magnet is replaced by a magnetic dipole. Okay? mu1. And this bar magnet is also modeled by another dipole, mu2. And both of these are vectors, by the way. Suppose we place this in a rigid frame so that this dipole does not move. We can place this in a vise or something, it doesn't move. And suppose this distance is capital Z. Oh sorry, small z. Now we would like to find the force that is exerted on this magnet. Now its potential energy of course is given by minus mu2 B at the point of this, at this point. We just assume that the area of this magnet is so small that we can ignore the variation of the magnetic field along the area of this dipole, right? So it's a small, it's spatially compressed, it's a small dipole. So that the magnetic field is constant all throughout this dipole. And that magnetic field is given by B. Now this B will of course depend upon Z, wouldn't it? Correct? So this B is a function of Z. Minus mu2. Now we already know what the magnetic field due to a dipole is. We've calculated this in class. This magnetic field is given by mu naught times this magnetic moment. Now this magnetic moment is mu1 divided by 2 and this distance z cube. Right? So we know what the magnetic field at this point B at this point Z is due to this source. Now this is the source of the magnetic field. It's a dipole and its field varies off as 1 over Z cube. And this is what the field is. Right? We calculated this in class. Now know that this is the permeability of free space. So don't confuse this with the magnetic moments. Okay. Now this expression, by the way, if you remember, is just analogous to the expression of the electric field from an electric dipole that is placed along its axis. And that's given by P, where P is electric dipole moment over 2 Z cube and an epsilon here. This is something we've also derived. Alright, so with this expression, the energy of this dipole at a distance Z is given by minus mu naught into the product of the individual magnetic moments divided by 2Z cube. Now stronger this dipole moment, stronger, the greater will be the energies, either positive or negative. Now we would like to find out the force on this object. So we know from classical mechanics that the force is given by minus du by dz. Correct? So if I know the potential energy and if I were to calculate the force, it's given by this expression. It's the variation of the potential energy with respect to distance. Remember that this looks very familiar to the expression that we've already seen. E equals minus dv by dx if we're talking about one-dimensional problems. So this is the electric field along the x direction and V is the potential. If I multiply both sides with charge Q, then this is the force on a charge equals minus the potential energy's gradient. So the electric field is really the gradient of the potential. And electric forces are gradients of the potential energy. So exactly the analogous situation applies to this particular case of a dipole placed inside a magnetic field. Now this force can be calculated from the derivative of mu, of u, and it turns out to be positive. Because there's a minus sign here and there's a minus sign here. Plus mu naught, mu1, mu2 over 2 the derivative of 1 over z cube, which is 0 raised to minus 3. Hence, this force turns out to be minus 3 minus 3 over z4 minus 3 over 2 mu naught, mu1, mu2 over z raised to power 4. Now force acts on this system, and that force is proportional to the product of the magnetic moments. Higher the magnetic moments, higher will be the field. Stronger the magnets, stronger will be the force of attraction. And it's inversely proportional to the fourth power of Z. This is really interesting. Now it's like a Coulomb's law, but it's not an inverse square Coulomb's law. There's a force between two dipoles, and the force is not proportional to 1 over Z squared. It's proportional to 1 over Z's fourth power. So you get an inverse quadratic law. It's not a Coulomb's law, but it's a Coulomb-like law. Now you have a force between two magnetic dipoles, and that varies as 1 over Z4. So larger this distance, the force will drop very sharply. So if I were to make a plot between Z and the force, that force is really going to drop really fast. So here I have Z. The magnetic field drops as 1 over Q. So this is the variation of the magnetic field, is 1 over Z cube. And the variation of the force is going to be even steeper. The force as a function of Z is going to be 1 over Z4. So that's why two magnets will attract one another only when they're very close together. And that is why we say that these magnetic forces, which are also called dipolar forces in this case, because they act between dipoles, these dipolar forces are short order. The dipolar forces act over only very small distances. So now what we've done, we've calculated the force between two dipoles. Now what I would like to move on to, any questions? कोई सवाल? Now I would like to look at some interesting observations about fields around conductors, magnetic fields around conductors. Current carrying conductors in particular. Now if I have current that is coming out of the plane of the blackboard, and it's a thin wire, really thin wire, so that its spatial extents is negligible, this wire will produce a magnetic field. We all know that. Now what's the direction of the field here? It's going to be circular and anti-clockwise, then we view from the front. Remember, anti-clockwise becomes clockwise, then we view from the other direction. So you really have to specify your locus of observation. Where are you observing the fields from? So in this case, the field is like this. Correct. Now if I have many current carrying conductors, all parallel to one another, and all of them are bringing current out of the plane of the blackboard, and they squeeze together very tightly, and the thickness of this section is infinitesimal, really small. Then what would the magnetic field look like? Could you please attempt at drawing what the field would look like? Good. Good. ठीक है, अब इसकी वजह से नीचे जा रही फील्ड इधर से ऊपर जा रही, क्यों? कैंसर field is actually going to look like this. So for this coil, for this current carrying conductor, the field is going to go circular and it's going to come around, but here it's going to point in this direction, but the field due to this adjacent current carrying conductor is pointing in the opposite direction. The field here is going to cancel out. So what, in the end you will get a bumpy kind of field like this. So here you will observe that the field lines are all pointing generally in the downward direction, and to the right they are generally pointing in the upward direction, with small kinks at the junction of two conductors. But if these conductors are really squeezed together in the perfect sense, this would make a sheet of current carrying wire, of current carrying sheet, right? A current carrying conductor which is a plane rather than a wire. So if I were to squeeze all of these together, and if I were to make this of infinite length, I would get a plane that is carrying current. And that plane, I can draw this plane in this particular fashion. Suppose this thickness is really small, it's negligible. But I have to draw some thickness for purposes of clarification. So there is current that is coming out of this wire, of this sheet. And this sheet is of infinite length. And if I were to draw the magnetic field lines due to this current carrying conductor, the field lines will be pointing in the downward direction. Now it's an infinite wire, so the field lines will actually extend all the way up to infinity. They will go all the way up to infinity, they will not go down. Just like you have an infinite plane of charge, its electric field is everywhere. It does not drop to zero anywhere, even though the field due to a point charge drops as 1 over r squared. But this magnetic field is going to point in the general downward direction, B1. And here it's going to point in the upward direction. And the field is going to be uniform. So it's not going to change with distance, and the field is going to be the same at this plane as it is at this plane, as it is at this plane. So it's a truly uniform field due to this infinitely sized current carrying sheet. So this field is B1, this field is B2. They are in the opposite directions, and we would assume by symmetry that B1 is the same as B2. Their magnitudes. Let's call this field B. Now I've given you the information that this sheet carries a current of K amperes per unit length. K amperes per meter. So instead of having a current density through an area, what I'm specifying here is a current through a certain length of this sheet. Which means that if I take a length of this sheet, which is L, then the total current that is passing through this length of the sheet is K times L. So this is my definition of a current density that I'm using here. Okay? And again it's a vector. It's pointing in the direction of the conventional current. So this kind of current density is called a sheet current density. Now what I would like you to do is actually find out the magnetic fields, B. What's the magnetic field in terms of K? And use Ampere's law. Current is coming out, I want to find the field here and the field here. Of course they're going to be the same in magnitude. And use Ampere's law. Your midterm exam was extremely good, wasn't it? Didn't you see the marks? आपका नाम हीरा है? हीरा कौन है? हीरा अकबर है आपका नाम? Extremely good. That's one ray of hope, a beacon of hope inside the class. There are at least some students who are doing really well. And those few students keep me going, in fact. But I'm here for everyone. It's up to you to learn. Why is there a 2 pi RL? Is there a cylinder that you're drawing? Why do you draw a cylinder here? An Amperian path has to be drawn, and an Amperian path is not a surface, it's just a loop. Good. Why is there a 2 pi r? Don't be stuck to formulas. I graded your midterms, you have a hangover with formulas. I want you to find a current due to a circulating proton, and you just look up a formula, I equals A N V D, etc., and just use that formula. It doesn't work like that. Think. Your starting point is your mind. Is the grey matter in your mind? It's not a formula that's in your hypothalamus, which is your memory. Alright? Think with your cerebrum. Do not invoke memory elements from your hippocampus. Think from your grey matter. No formulas. This is not Ampere's law. This is not Ampere's law. So I know what the magnetic field pattern is going to look like. It's going to look like this, downwards here and upwards here. Now the field is B, capital B, its magnitude is B everywhere, even though it's pointing downward here and pointing upward here. Now for application of Ampere's law, I have to draw a closed path, not a surface, but a path, a circuit, a loop. And now something that I would like to draw in this particular case is not a circle, because the circle is curved. And here the magnetic field lines are just vertical. So I would like to draw a square or a rectangular path. And the kind of path that I draw is like this. It's a vertical line here, horizontal line, vertical line, horizontal line. So it's closed. And the direction which I traverse the loop is the conventional. If I look at it from this perspective, it's in the anti-clockwise fashion. I go down here, here, up here, up here. Now this is my loop. Now around this loop, B dotted with DL, around this loop is given by. Now here I am traversing the same direction as the magnetic field. So, and the length of this loop is, say, small l. So here the dot product is locally going to be positive, and then I integrate from this point to this point, I get plus BL. And here, once again, I am traversing the loop in the same direction as the magnetic field. So I get another B plus L, so I get 2BL. Correct? Now, along this section, the field lines are all normal to the direction of traversal. So the local dot product is 0. So along this section, the dot product is locally 0 everywhere, and here it's 0. So I do not get any contribution from these paths. So this 2BL equals, according to Ampere's law, mu naught times the current enclosed. And what's the current enclosed here? K times L. So my magnetic field B, this magnetic field, its magnitude is mu naught K over 2. So here the field is pointing in the upward direction, so the field is mu naught K over 2. If this is my Z direction, K unit vector. And here the magnetic field is minus mu naught K over 2 unit vector K. So now if I were to make a plot of the magnetic field, this is my Z axis, this is my Y axis. So if I were to make a plot with respect to Y of the magnetic field, and I can only make plots of scalars, not a vector, so I drop out this K and I make a plot. Here the field is positive, which is in the upward direction. Here the field is negative, and this point is mu naught K over 2, and this point is minus mu naught K over 2. And there is a discontinuity in the magnetic field, and the amount of this discontinuity, this jump, is simply mu naught K. Now look at this scenario from the concept of a charged sheet. If I have a charged sheet, positively charged sheet, the electric field is going to vary. Now in this case, the electric field is pointing in this direction, normally outward from the surface of the charge. Now these electric fields have the same magnitude even though they are pointing in opposite directions. Now compare this situation with this situation. An infinite sheet of charge has electric field lines that are normal to the surface. Alright? Here the magnetic field lines are tangential. They are just along the surface or parallel to the surface of the sheet. In this case, if I were to make a plot of the electric field's variation with Y, alright, then the electric field here is going to be positive, here it's going to be negative. Here, what's the electric field here? If this surface charge density is sigma, what's the electric field here? Sigma over 2 epsilon naught. So here the electric field is sigma over 2 epsilon naught. Here it's minus sigma over 2 epsilon naught. And totally analogous situation. And the amount of jump that we have, the discontinuity we have, is sigma over epsilon naught. So the amount of charge per unit area determines the discontinuity in the electric field. And there's 1 over epsilon naught. Here, the amount of discontinuity in the magnetic field is given by the sheet current density. How much charge is flowing through the sheet per unit area into mu naught. And look at the correspondence between mu naught and epsilon naught. Whenever mu naught appears in the numerator, epsilon naught pops up in the denominator. So they have a kind of inverse relationship, mu naught and epsilon naught. In fact, if you take mu naught and epsilon naught and multiply the two together, this product is always going to be equal to 1 over square of the speed of light. Okay? So epsilon naught and mu naught are like seesaw. One is in the numerator, the other is in the denominator. So this is an effect that whenever we have a charged surface, the electric field lines are normal and the amount of discontinuity tells you the amount of charge per unit area. Whenever you have current coming through a sheet of wire, the field lines are parallel to the sheet. They're not normal, they're parallel. And the amount of discontinuity is equal to the charge, the current that's coming out and going in. Now in electrical circuits or computer circuits, you have what are called copper buses or bus bars. So instead of having wires, you have current that is coming in a plane. And generally, you have in your motherboards or other kinds of circuits, you have copper bus bars that come in pairs. So current, a power line that's coming, bringing current out, and a power line that's taking current in. So here the current is coming out. And we assume it's of infinite size. Here the current is going in. Now what does the magnetic field look like? If this current sheet density is capital K, this is minus K, the same amount of current coming in, coming out, coming in, what would the magnetic field pattern look like on this side, as well as in between the pair of copper bus bars? किस डायरेक्शन और बाहर क्या होगा? What's going to happen outside the pair of copper bus bars? There's going to be no magnetic field. The magnetic field will only exist within the confines of these copper bus bars. So there will be some field here. So this field will be pointing in the downward direction. And it's going to be a uniform field, because of the infinite size of these conductors. Upwards. Alright. Upwards. Here, there will be no magnetic field. So why isn't there any magnetic field outside the copper bus bars? Why isn't there any magnetic field here? Could you give a shot at this answer? आप बताओ जी यहाँ पे मैग्नेटिक फील्ड क्यों नहीं होगी? Right. The magnetic field lines due to this copper bus bar, they are in the downward direction here, and due to this copper bus bar, they are in the upward direction. Now you can argue that this point P is closer to this current carrying wire and it's further away from this current carrying sheet, but that does not matter because these are infinitely sized sheets. It's a perfectly uniform field. So you can apply the principle of superposition. These fields are totally opposite to one another, so this field goes away. And if you were to plot the magnetic field's magnitude in between or in this geometry, it's going to look like this. Here the jump is mu naught K. And here the jump is minus mu naught K. So it's a downward jump. So this current coming out gives you a positive jump. This current going in gives you an opposite jump. Just like a negative sheet here will invert this graph. The jump will be negative. Alright? So there will be no magnetic field outside this copper bus bar. Now suppose I have a situation like this. I have some conductor, a sheet that is bringing current out of the plane of the blackboard. Now this is something really interesting to observe. Suppose I have some external source of uniform magnetic field. Now this current carrying sheet will produce a magnetic field of its own, given by this configuration. Now is it possible to have a configuration of this kind? A field configuration, a field pattern of this kind. Suppose I am ignoring the thickness of this sheet. Can I have a magnetic field of this kind? And if this is the magnetic field, what's the direction of the external magnetic field that I've superimposed upon this geometry? Exactly. So what I've actually done, on top of this magnetic field, I have inserted an external magnetic field that's pointing in this direction. B external. And since both of these are vector fields, at each point I will take the vector sum of the magnetic fields. Here, these field lines that are in the upward direction, they will shift towards the right. And the amount of shift will depend upon the relative magnitude of the external field and this field. Alright? And actually, by looking at this angle, theta, you can tell out the relative ratio between these fields. Likewise, on this side, the field lines are pointing downwards due to this current carrying conductor, but on top of it I superimposed an external field. So the field lines are going to tilt upwards slightly. This is what is happening. So the field lines are downward, but they're going to tilt in the upward direction. So this point is in fact a vector sum of the field due to the sheet, B due to the sheet, plus the externally applied field, B external. And the net field is like this. For the same reason, it's impossible to have a magnetic field. You have a current carrying conductor that is carrying some current in any direction whatsoever. It's actually impossible to have a magnetic field pattern, a net magnetic field pattern of this kind. It's impossible to do that. Impossible. Just as if you have a sheet of conductor and it's in a state of equilibrium and there's no charge on this conductor. Suppose the current density is 0. There's no charge that is stored on this conductor. It is impossible to have an electric, there are certain impossibilities. There is no electric field normal to the surface of the conductor because this is 0. And it is impossible to have an electric field parallel to the surface because this electric field will cause charges to flow, but that's not possible because it's a condition of static equilibrium. If this was charged, if this were a charged sheet, it had some charge. Suppose that charge density was uniform, sigma naught. It can only have electric field lines that are locally normal to the surface. It cannot have an electric field line that is at a slanting angle to the surface. This angle always has to be 90 degrees. You cannot have a non-90 degree angle here. Because if such a field were to exist, it would have a component parallel to the conductor which will cause charges to flow. So such a field that is not normal to the surface of a conductor is impossible if you have static conditions. So there are certain impossible electric or magnetic fields. For example, if you do not have a changing magnetic field, I've already shown you that it's impossible to have an electric field like this, right? You cannot have a tangential electric field if there are no flowing changing magnetic fields. This is Maxwell's equation. This is Faraday's equation, the partial form of it. Right? So this simply is E dotted with dl around a closed path is 0. The partial Faraday's equation. So this again is an impossible electric field. So the world of magnetic fields and electric fields is extremely rich, extremely diverse, and it has huge practical applications. Now let's look at some more examples. Let's gather all our scattered concepts. By the way, is the attendance sheet circulating? Alright, it's done. Let's gather all our scattered concepts. जमा करें सब चीजों को जो इधर-उधर बिखर गई हैं ना, उनको थोड़ा जमा करके हम एक चीज को विजुलाइज करने की कोशिश करते हैं. Suppose I have a current carrying conductor. Alright, so it's carrying current in this conventional direction, I. So we have a current density J, which is locally normal or parallel to the axis of this bent conductor. This is J. Now first of all, let's find out the electric fields inside and outside this conductor. Now what's the direction of electric field inside the conductor? Syama. It will be parallel to this current density. No, it's J is conventional direction. It's going to be parallel to this J. And will it be axial? The electric field is going to be axial, parallel to the axis of this conductor locally, right? So the electric field is going to be like this here, it's going to be like this here, it's going to be like this here. Right? So it's just going to be a streamline of electric field, and it's like a tube of electric field lines. All of them are parallel to one another. Alright? बिल्कुल इसी तरह देखेंगे अगर ये पानी का एक पाइप है और इसमें से हम पानी गुजारते हैं किसी स्पीड से, and if you have filaments in this pipe, all of them will be parallel to one another. Alright, so this is the electric field inside this conductor. What about the electric field outside the conductor? Will there be an electric field outside the conductor? Now you have a wire that is just transporting current. Will there be an electric field outside the conductor? I give you half a minute to think about this. अब अपने peers से discuss करें, साथ वाले से discuss करें, and then I'll ask you if there would be an electric field outside the conductor. वो चार्जेस स्टैटिक चार्जेस पूरी बात डिस्कस करें. ये करंट क्यों फ्लो कर रहा है? चार्जेस तो फ्लो कर रहे हैं लेकिन सरफेस पे कोई चार्जेस हैं या नहीं? ये पॉजिटिव चार्जेस का फ्लो दिखा रहा है J, right? Conventionally. जी उम्र पर होगा, ये कैसे? हाँ तो पॉजिटिव होगा इधर नेगेटिव होगा। हाँ तो सरफेस चार्जेस तो होंगे लेकिन यहाँ नेगेटिव थोड़ी होगा, ग्रेडियंट होगा अलॉन्ग द लेंथ। आगे समझ आ गई कि इलेक्ट्रिक फील्ड बाहर कैसे होगी? नहीं पता चला क्यों नहीं होगी? नेग्लिजिबल, चलो आप नॉन नेग्लिजिबल है। यार ये तो हमने बड़ी डिटेल में देखे सरफेस चार्जेस बनते हैं। Zen? Any ideas? Alright, so this is a recap, a revision of what we've learned. Why is there an electric field inside the conductor? The electric field has been produced due to negative feedback. What has that resulted in? Surface charges. Now there are surface charges on the surface of this wire which steer the current through the wire, which produce an electric field inside the wire, which causes the current to flow. Without this electric field, J cannot exist inside a conductor. So there has to be an electric field. Now that electric field has been created by negative feedback in the process of a transient, and that has resulted in charges accumulating on the surface of this conductor. They could be really small charges, but they are still there. They are required to produce this electric field. We've already seen that. So if electric field is in this general direction, this means that the charges are such that there is a gradient of surface charges along this length. There is a potential difference along this length, which means that there will be higher accumulation of charges here, all on the surface, right? There will be charges on this lateral surface as well, but I'm not drawing those. So there will be charges everywhere on the surface. Here there will also be charges, but the charge density could be slightly smaller. Here it could be even smaller. Here it could be even smaller. Then you can have negative charges building up, right? So you can have concentrated to dilute positive charges, then dilute to concentrated negative charges, and then you finally reach the battery. So there are positive charges here everywhere, or there could be negative charges everywhere, but that does not mean that there is positive charges here and negative charges here, right? That's impossible because it's the surface of a conductor. So there is a charge density gradient along this surface of this conductor which produces the electric field in the first place. Now these charges are really small. We've learned about these surface charges. Don't undo what you've learned so far before the midterm. The midterm is not a watershed in the discussion of electricity and magnetism. All physics, all science is a continuum, right? So these surface charges do exist. Now they're really small, so they produce their own electric fields. Now their electric fields will be really small because the charges are small. We've already seen that we require just one electron to steer a current of 1 ampere through a bend. These charges are so small. And you know that if you have a single electron, if you were to find out the electric field due to that electron, it's going to be 1 over 4 pi epsilon naught. The charge on an electron divided by, if you're at 1 centimeter away, say 0.01 squared away, you'll find out that this electric field is really small. It's of the order of, say, a 10 raised to power minus 10 volts per meter. It's really small. But nevertheless, these charges will produce an electric field. Okay? Now, this electric field inside the conductor, this electric field cannot go inside the conductor because we know that these are static charges. Remember, these are static charges. In steady state, the distribution of charges does not change because now the current is steady. It has reached its steady state. It's a stationary current. The amount of current is not changing, which means that the electric field inside is not changing. Whatever electric field has been set up remains there. And remember, the electric field is parallel to the surface. It's not normal to the surface. This electric field is along the axis. But so these charges will produce their electric field, but none of that electric field goes inside the conductor. Because these are static charges. We know that whenever you have charge distributed on the surface of a conductor and it's static, it will not, the field will not penetrate inside the conductor because it will violate Gauss's law. There are no charges inside. All of them are on the outer periphery. So there will be an electric field, and that electric field is going to be radially outwards. So it's going to be radially outwards. At each point on the surface, there's going to be an electric field pointing radially outwards. E out. And this is due to the static charge. And this is going to be a really small field because these charges are really small. So there are no fields inside due to the static charges, but there are fields that are normal to the surface of the wire and pointing outwards. So if I were to draw a section of wire here, if I were to cut up a section of the wire here and cut up a section of the wire here, let's call this section A and let's call this section B. If I were to draw a cross section of the wire at A, and if I were to draw a cross section of the same wire at B, here there are surface charges. Here there are also surface charges, but they will be diluted than this. Okay? So the same surface area but fewer charges. Now there's going to be an electric field, this yellow electric field that is making the current flow, that has been set up because of the difference of these surface charge densities. That electric field, say, is pointing in, right? This is due to the potential gradient of the surface charges. The same electric field is in here because the current is uniform. But these charges that are on the surface don't change with time because the electric field has already been set up. And these charges will produce an electric field that is locally normal to the surface and pointing outwards, not inwards. So these charges will be producing an electric field pointing outwards. And this electric field is going to be really small, but it's nevertheless going to exist. Because without this, we cannot explain how energy is transported inside circuits. And I'll have one lecture on this. These electric fields that are on the outer surface and pointing outwards from the wire, they're really small and they are static charges. This electric field is just going to be sigma over epsilon naught. If sigma is the charge density here, the electric field is going to take up this value, sigma over epsilon naught. Here there will also be an electric field, but since the charge density is smaller here, so the field is going to be pointing outward, but nonetheless it's going to be smaller in magnitude. So this is the distribution of the electric field inside and outside the current carrying conductor. Now I would like to talk about the distribution of magnetic fields around this conductor. So an extremely simple object like this wire, which has a current flowing through it, has a rich structure of electric and magnetic fields that surround the wire. What's your question, Usman? But there's electric field everywhere inside it. Because that makes the current flow. And that electric field is produced because the amount of charge here is different from the amount of charge here. Right? These surface charges produce this electric field. That electric field is everywhere inside the conductor, not just at the center. Okay? Now let's discuss the magnetic fields around this current carrying wire. Any questions about the electric fields that surround this wire? तो बहुत से बारीक बारीक नुक्ते यहाँ छुपे हुए हैं, ठीक है, जिनको आपका काम है इनको देखना, ठीक है। ये बादी नजर में ये नजर तो आता है कि कुछ भी नहीं है, आप बैक ऑफ द चैप्टर प्रॉब्लम सॉल्व कर लेंगे तो you'll be happy, but there are really subtle points, subtle nuances that a designer or an engineer or a scientist or a physicist should actually be cognizant of. And this is the spirit of physics. G. The current is flowing throughout the entire volume. It's going to flow at the surface as well. It's a DC current, so current is flowing throughout this volume. For AC, however, for higher frequency, there are cases when the current only flows on the surface. That's called the skin effect, and we'll learn about this. Now, what we would like to do is find out the magnetic fields around this wire. So let's draw, first of all, as we've done for electric fields, I would like to find out whether there exists a magnetic field inside the conductor. Now I'm drawing a cross section of the conductor. Current is coming out. बहुत बारीक बारीक टूटते हैं, इनको देखना चाहिए, ठीक है। और उसके लिए आपको वक्त चाहिए, उसके लिए आपको सुकून चाहिए, उसके लिए आपको जो दूसरी डिस्ट्रैक्शंस हैं उससे थोड़ी सी देर के लिए अपने को अलग करना पड़ेगा, फेसबुक से अलग करना पड़ेगा, ट्विटर से अलग करना पड़ेगा अपने आप को, उसके बगैर नहीं आएगी ये चीज। और थोड़ा सा इम्तिहान और मिड टर्म और ग्रेड से ऊपर होकर सोचना पड़ेगा। You have to transcend these little petty things of grades, at least for half an hour in a day. Just transcend above those. Life is too beautiful to be messed up with grades and midterms and exams and GPS. Now, if you have this current carrying wire that is bringing current, suppose current is coming out, okay? Or let's use this same current is going in. So the electric field is in, so the current is going in. So now I'm plotting the direction of the current. This is J. Electric field going in, current going in. First of all, I would like to find out whether there is a magnetic field inside the conductor or not. बाहर तो बात की बात है. Let's find out whether there is a field inside. And the radius of this conductor is capital R. The current is steady and it's uniform. So at each point the current density is the same because the electric field is the same. Now, will there be a magnetic field inside the conductor or not? There was a recitation question to this effect as well. आप बताओ, अंदर फील्ड होगी मैग्नेटिक फील्ड या नहीं होगी? ठीक है. Is there any argument that there will not be a magnetic field inside the conductor? Any disagreements with this thought? जी, क्यों नहीं होगी? नहीं होगी फील्ड अंदर, क्यों नहीं होगी? एक पॉइंट पे फील्ड किससे कैंसिल आउट कर देते हो? सात वजह से. Stop relating to it. Let's draw, whenever we have run into problems of this kind, let's use one of Maxwell's equations to our rescue. Let's draw an Amperian path. And if we were to draw an Amperian path, what would that path look like? It would look like a circle. And we would like to make the center of that circle concentric with this wire. So let's draw a circle, an Amperian path of radius small r. Now there will be an electric field inside, magnetic field inside this wire because there is charge flowing. Whenever there is charge flowing, there has to be an electric field. At the exact center, you can say that there is current up and below, and there is current to the left and to the right, and all of these contributions will cancel out. So the expectation is that the magnetic field will be zero at the center, but not at any other point. The magnetic field will be non-zero at any other point. And if you draw a circle whose center is the axis of the conductor, then if there were a magnetic field, it's going to be the same here as it's here, as it's here, because of the symmetry of the problem. It's a circular conductor. And let's look at, now if you draw this circle, there is current coming out. And this current that's coming out inside this conductor is going to produce a magnetic field, current going in, is going to produce a magnetic field in the clockwise fashion. So this is the direction of the magnetic field, B, at a distance r from the center of this conductor. And there will be contributions from outside this conductor. So there will be contribution from this filament, a contribution from this filament at each point, and all of these will create a magnetic field here. But what we are interested in is finding the line integral of this magnetic field on this path. And we know that the magnetic field at any point on this path is going to be the same. And by symmetry we know it's going to be tangential, it's going to be circular. There's no other direction that this magnetic field can point in. So if we were to apply Ampere's law here, B, whatever this field is, BR into 2 pi r. Now what's the relative angle between the direction of traversal of this path and the field? The path is always traversed in this anti-clockwise fashion. So I would like to put in a minus sign here. Okay, that just shows the direction of the field, nothing else. If the field were in the opposite direction, it would be positive sign here. I'm only interested in this magnitude nevertheless. So this equals mu naught times the current enclosed only inside this area, which pierces this area on whose outer periphery lies the path. So that area is, that current is the current density J into pi r squared, which is this area, the area that I'm slightly shading here. This gives us the magnetic field. So this magnetic field BR turns out to be minus mu naught J pi r squared divided by 2 pi r minus mu naught J r over 2. So if I were to make a plot of the magnetic field versus the distance from the center of the conductor B, and if capital R is the radius of this conductor, this field is increasing linearly. So inside the conductor there is indeed a magnetic field. You cannot stop this field. This field will exist. It's going to be zero at the center of the conductor because of the argument that I saw here about cancellations. But then this field is going to ramp up. It's going to reach a maximum value at capital R. And the direction of this field is tangential. Now if I were to find out the field outside the conductor, the magnetic field, it's quite simple. You've already done that. It's going to be, once again I use Ampere's law, B into 2 pi r divide equals mu naught times the total current enclosed by this conductor, which now is J into pi capital R squared. This means that B as a function of R, this is R less than capital R, this is R greater than capital R, is mu naught J R squared over 2 small r. Now you will see that the dependence is 1 over r. So the field is now going to drop outside the conductor and it's going to drop off as 1 over r, like this. This is proportional to r. This is proportional to 1 over r. So this is how the field is going to change outside this current carrying wire, the magnetic field. Now in the last 2 minutes I would like to draw a pattern of this field. So this is my current carrying conductor, a cross section of it. And now what I'm going to draw, first of all I'm going to draw the magnetic field inside. So inside, here the field is 0. Outside, right, the field is tangential. inside, it's tangential. At some other point, which is at a greater distance from the center, the field is going to be larger, but still tangential. So now I'm drawing electric field line, magnetic field line. It's going to be larger, so that's why I've drawn bigger arrows, because the field is going up. Here the field is even going to be stronger. It's going to be strongest at the surface. Now outside, the field, magnetic field is going to drop once again, and it's going to drop in a hyperbolic fashion. So here is some magnetic field. Again it's tangential, circular or tangential. Then the field is going to drop. But still it remains tangential because of the symmetry of the problem. And on top of this, you have the electric fields. You have an electric field pointing into the plane of the blackboard inside the conductor. And you have electric fields that are pointing normally outwards, outside the conductor. And this combination of electric and magnetic fields in fact makes energy flow inside the circuit. And when I talk about pointing vectors, this is what I'm going to deal about it towards the end of this course. So in the next two lectures, I'm going to talk about magnetic materials, and I'm going to show you demonstrations on superconductors, and I'm going to talk about ferromagnets, paramagnets and diamagnets. And there will be a quiz next Friday, the third quiz, and I'm going to post an additional homework probably today or tomorrow. Thank you very much, and see you on Tuesday inshallah.